Okay, well, who prepares? Right. So now we're gonna have Jules Hedges, who's going to give a series of lectures about applied category theory.
Thanks. Hi, I'm Jules. A few weeks ago I had COVID and I'm not over the exhaustion yet, and the exhaustion hit me like half an hour ago, so hopefully the adrenaline will carry me through this. Let's see how this goes. So I should start by talking about what the topic of this is. So I named this course Applied Category Theory, and that's named after a research field that we call Applied Category Theory, which has an associated conference which we call Applied Category Theory, which has existed since about six years ago, I think. 2018, I think we had the first conference and we had a public debate about what we should call the field, and settled on this name. And I've come to think that this is a bad name eventually, because what is applied category theory? Well, so if you draw a Venn diagram of applied category theory and category theory that is applied, they non-trivially overlap, but then they're far from the same thing. There is category theory which is applied, which somehow doesn't fall into the field that's called applied category theory, such as, for example, a whole bunch of stuff in semantics of programming languages is pretty clearly applied in any kind of reasonable sense. But meanwhile, stuff gets labeled applied category theory that doesn't look very applied at all. So the reason this field came into existence was because some people noticed that a bunch of different groups were working on things that were weirdly similar to each other, coming from different directions, and it was all about using structured monoidal categories for things. Using structured monoidal categories to think about systems or processes or something like this, with a heavy emphasis on compositionality. So compositionality is reasoning about how a thing is built up of parts, right? In everyone here is a computer scientist, and in particular a theoretical computer scientist, and so this is such an obvious idea that it's we can just forget that there is such a thing as compositionality. It's so much second nature. Then you open an engineering textbook, and your soul drains away from your body. Kind of what applied category theory is often trying to do is to bring the benefits of compositionality, which are so fundamental to computer science that we forget that they exist, to fields that don't have it. So what this course is going to be about is a lot of stuff about monoidal categories, symmetric monoidal categories in particular, and stuff you can do with them. It's not going to be as applied as I would like applied category theory to be. That's partly because it's an introductory course, so I have to cover foundational stuff. It's partly because, it's a hot take of mine that the art of applied category theory is to know when to stop doing category theory and get your hands dirty and just write a bunch of Python code or something. I don't know. Yeah. Okay. Around 2015, 2018, around that time, people noticed that people coming from different fields were coming up with category theoretic structure that was weirdly similar, and so this field was born to take advantage of the fact these are the same. So, for example, there was people developing categorical quantum mechanics, ZX calculus. This is a graphical calculus for thinking about the processes that you can run on a quantum computer, aka quantum circuits, so things that you can apply to qubits. Simultaneously, so they were kind of based in Oxford and places which were kind of logically connected by people to Oxford. And then simultaneously, there was a bunch of people in California based around kind of John Byers' group thinking about general systems theory, so open systems, and how open systems compose together. And John kind of heavily emphasized that stuff. Simultaneously, as well, there was people around, for example, Paweł Sobocinski, doing graphical linear algebra and applications of this in electrical circuits and a bunch of other applications. And people noticed that the same mathematical structures came up in all of these places. There was also like me doing game theory and some related things. There was some machine learning stuff going on around that time, which, no surprise, kind of took off a lot. 2018 was a funny time. Yeah, so there were common mathematical structures which were largely structured monoidal categories, and so this field that people call applied category theory kind of took off, focusing on things you like, ways of thinking about structured monoidal categories and things you can do with them. So, okay, so how I'm going to structure this course is roughly lectures 1, 2, and 3 are going to build a cohesive story of building up additional levels of structure you can put onto a symmetric monoidal category that sort of refine each other. So each is a special case of the previous one, and I'll regularly stop to give examples and show interesting things that you can do by thinking about those examples. So that's kind of motivation for thinking about that structure in particular, rather than jumping all the way to the most general one. And then lecture 4, I'm going to do something that's kind of branches off slightly differently, where I talk about my own stuff with applications in machine learning and a few other places. Okay. So that is to say, so all of that is a very long-winded way of saying that the name of this course is slightly inaccurate. The category theory part is accurate. The applied stuff is on thin ice. But we'll see. You can judge how applied you think this is. And yeah, my intention is to do a relatively broad and shallow course. So I say a little bit about a lot of things rather than a lot about a few things. English is weird. Yeah. Okay. So that's kind of intentional. But for the first 3 lectures, I'm trying to emphasize the recurring structures. This first lecture is going to be about string diagrams, and in particular, the theme of the first lecture is why you should consider string diagrams to be syntax. Like, string diagrams are very. I skipped Chris's lectures. I know Chris. Thank you, Chris, for covering a whole lot of this in advance. But in the first lecture, I'm going to focus a lot on string diagrams. So the theme is why string diagrams are perfectly good syntax despite not looking like strings of symbols, despite not looking like syntax in any kind of familiar way that you learn from an undergrad course in logic or programming languages or something like this. Okay, so you all know what a string diagram is, but like, here's a motivating example, and I actually just looked this up in Brendan Fong and David Spivak's book, 7 Sketches in Compositionality, because this is a famous example, and it's about cooking, and I'm a terrible cook, so I couldn't remember it, and I had to look it up. They have a famous string diagram for how to make lemon meringue pie, and this motivates the idea that string diagrams are a kind of resource theory, that you have an egg, right? And then, so this is a resource, and then you apply a process to the resource, namely you separate it, and now you have, in fact, I'm going to say you get 3 outputs, which is you get the egg white, you get the egg yolk, and you get a shell. And we're not going to need the shell for anything else, so we're going to throw it in the bin. right? That's a process that I'm applying to that resource. And now now I've already forgotten from 10 minutes ago when I looked at the string diagram how to make them a meringue pie. But I think the idea is that you take the white with some other stuff and you do some other stuff. And then you take the yolk with some other stuff and you do some stuff, right? You know, stuff, what people do in kitchens. And then, and then, right. And then I think at some point, right, you have an oven, and you cook, and here you get your lemon meringue pie, but you still have an oven at the end, right? You hopefully. I mean, if I did it, I might not, but. Actually, I'm going to jump several pages ahead in my notes to say the following sentence. So, the fundamental non-theorem of applied category theory is that everybody understands string diagrams intuitively, even if they don't know it. You can show this to your boss, right? If you're a management consultant, you can show this to your client, and they know what you mean. If you gave them one-dimensional syntax, the kind of syntax that you do normally, like syntax of programming languages, logics, that type of thing, they'd be like, "The fuck is this?" But this is intuitive. Lots of people have independently invented this idea. There's flowcharts, computation graphs, you go and program your favorite game engine, you end up scripting NPC behavior in your favorite game engine using things like this, right? And those people didn't study category theory; they just independently invented it because it's such an obvious idea. And so it's so intuitive that people understand it without even knowing it, but it is a completely formal, precise syntax. We can prove theorems about it. So it's the best of both worlds. It's unambiguously precise, but also intuitive. It's so in my opinion, applied category theory of the field is kind of founded on this idea. Having shown you what a string diagram is by example, now I'm going to say something about what it really is. So a string diagram is a presentation of a free monoidal category. And the answer to when someone says that something is free, the answer is free on what? So the answer is free on a thing called a monoidal signature. And I'm going to define what a monoidal signature is. That's not the best color. Okay, a monoidal signature is, so this is the generating data of a string diagram, and what it's going to be is it's going to be the sets of stuff that can label elements of your string diagram. So I drew this thing, and then in the boxes I was writing the names of processes like cook, and on the wires I was writing names of resources like egg. And where do these come from? They're elements of some set which is a part of a monoidal signature. And this is basic. I mean, this is the same thing as signatures in logic, right? Like you learn an introductory first order logic class, you get signatures that contain function symbols and that type of thing. It's the same idea. So it consists of, call it sigma, of a set of object symbols. I'm sorry, my handwriting is bad. I should slow down. That says object symbols. A set of morphism symbols and now So for each morphism symbol, we need to say what is its domain and codomain. We need to give its type. And its type, well, you might think that its domain and codomain should be objects, but this is a monoidal world. Its domain should be a tensor product of objects. So what we're going to do is functions source and target, which go from the morphisms of sigma to lists. And what's special about lists? Well, lists are the free monoid on a set. So the idea is that a list x1 ... xn is, I'm thinking of this as a formal tensor product. So the idea is now that if I have some f in my set of morphism symbols, so now f is really syntax, right? Like this is a set of syntactic things. It's these are just things that can be either equal to each other or not. There's no other properties that they have. And I'm going to say that the source of f is going to be some list x1 up to xn, and the target of f is going to be y1 up to yn. Then this means that I can draw a string diagram element where the incoming y's are in order x1 up to xn, and the output y's are in order y1 up to yn. So the signature is basically saying what the string diagram looks like locally. If I zoom in on one particular node, this gives the kind of typing constraints. Here is the incoming wires in this order, and here is the outgoing wires in this order. Okay, there is some conventions going on which I should say something about. So I'm choosing a left to right convention here. So my morphisms of a category are oriented from a source direction to a target. Yeah. Oh, sorry, no, that is not true at all. Right, these are just two arbitrary lists. Of course, the list could be empty. M and or n could be 0, in which case the empty list is kind of standing for the monoidal unit. Okay. Okay, so I have an orientation from left to right. The main advantage for choosing a particular orientation is in order to start flame wars on the internet. Of the 4 possible ways of orienting a string diagram, 3 are in widespread use. So top to bottom is very common. Bottom to top seems a bit surprising, but Feynman-oriented Feynman diagrams bottom to top. So a bunch of physicists follow Feynman in that. The only orientation that I've never seen used is right to left. But I'm still hoping for someone, like a group who works in a place where they use a right to left written language, to invent that so that we can complete the set. Okay, the other thing I should say is that if you're being very pedantic about what string diagrams really are, this rectangle is really a 0-dimensional point. So it's like a graph. So can everybody see? Yeah, should be okay if I write that low.
Yeah.
If you're extremely pedantic about foundations, string diagram nodes should be 0-dimensional, like we draw for graphs. This convention is helpful and isn't really a problem. We can just, without loss of generality, assume that each node has some finite region of space to itself. Okay, so string diagrams are in many ways graph-like. They're different to graphs in a few ways. So probably the most important way that string diagrams are different to graphs is that, so in a graph, a node has a bunch of neighbors, right? Okay, maybe it's a directed graph, so a node has a bunch of incoming edges and a bunch of outgoing edges. Come on, I can reverse my brain. Incoming edges and outgoing edges. But in a graph, the incoming and outgoing edges form a set or multi-set. Like the swapping them around makes no difference. Whereas in a string diagram, we consider the ordering of these things to be important. The reason we consider the ordering of these things to be important is that these morphism symbols might stand for some semantic operation which might not be commutative. So we really need to keep our inputs in order. Okay. I might as well also mention, so the definition of monoidal signature. So this definition was written by Joyal Street in their paper in 1980, either 7 or 8 or 9, I think, one of those, which stated and proved the coherence theorem for monoidal category for string diagrams, which I'm about to come to, but I think Chris already touched on this. They just wrote down this definition that this is the generating data of a free monoidal category, but it's suspiciously similar to a few other things. So if you're slightly opinionated about your definitions, you can say that this is the definition of a Petri net. That's not a coincidence, but I'm not going to go into that. So this is like so Petri net has things called places and transitions, and each transition can go from a whole bunch of places to a whole bunch of other places. And so it says that I take in resources from these places and I add resources back to these places. If you don't know what a Petri net is, it's a monoidal graph, a monoidal directed graph. So in other words, it's kind of the halfway point between a directed graph and a monoidal category. It's also, if you're very opinionated and take risks with terminology clash, you could call it a directed hypergraph. So it's like we have some nodes and we have some hyperedges, and each hyperedge goes from an ordered list of input nodes to an ordered list of output nodes. I don't recommend referring to this as a directed hypergraph because there's like 5 different things that the word directed hypergraph can mean. Yeah, that's why I said you had to be opinionated about it. In my opinion, this is the correct definition of a Petri net, but people who work with Petri nets can disagree with that. Right. So here's the thing. I'm jumping ahead slightly, but this is also the generating data for a symmetric monoidal category. So even when we care about symmetry, we still use ordered lists. Yeah. So this is about whether swaps are implicit or explicit. Anyway, okay. All right. Okay. Now, what time is it? Okay. Good. I should speed up. Of course, I should speed up. I haven't timed this, so. All right. Okay. So what is a string diagram? Well, it's this kind of, it's a graph-like thing, except that we consider the ordering. So it's like a graph equipped with an immersion in a plane. So, and it's not an abstract graph, it's a drawn graph. There's a technical, pure mathematicians have a technical term for, they're called maps, I think, like a graph that is actually equipped with an immersion in the plane. Where we consider the orderings of these edges of nodes to be important, and also we have this condition that we call progressive. So being progressive, there's my eraser, says that we are not allowed to do that. or that. So my edges can strictly go from left to right. So I can wiggle like this. That's okay. But I cannot turn around. So, for example, I cannot connect a codomain back to a domain like that today. Tomorrow, we're going to do that kind of thing. So what does this mean? Well, one way of defining this, you can define this in a few ways. It doesn't really matter. They're all equivalent. The most straightforward way I know how to do it is to say that this graph is equipped with a topological ordering. So it says that's the kind of before relation. And this says that you can draw a wire connecting the codomain of some node to the domain of some node that comes strictly after it. So that's enforcing a left to right ordering on these things. So this is a kind of causality condition. It says that the things that we can draw in a string diagram are causal. And you kind of if you remember the meringue pie string diagram, this is kind of causal. I have to by inspecting this and by reading it from left to right, I can see what things I have to do before I can do other things. The processes become prerequisites for other processes by being to their left. Okay, cool. Now, maybe I do the next part in a different order from what I planned. So I plan to, so in my notes, I now have a whole bunch of monoidal categories that I think are interesting. And then later talk about the coherence theorem for string diagrams. So this is the fact that string diagrams mean things in monoidal categories. They have semantics. But maybe I'll swap this over. So at the moment, just keep in mind that there are many examples of monoidal categories and symmetric monoidal categories that are interesting and that we care about. And you can, for now, take that on faith. And then later I'll talk about a bunch of examples. So let's talk about let's skip forward. Yeah, okay. Yeah, it's true. Yeah, okay. So I can go very quickly over this, can't I? Yeah. Yes. Right. So okay. So suppose I have a monoidal signature. Okay, you're seeing this for the second time today, I guess. But so I'll go over this quickly. We have a monoidal signature, and I have a monoidal category. Let's call this. Okay, I'm going to make this a symmetric monoidal category. And I'm going to define a thing called evaluation of sigma in C. So it's unsurprisingly similar to stuff that Vikram was talking about an hour, 2 hours ago. It's a function from the objects of sigma to the objects of C, and from the morphisms to the morphisms, such that, well, you can guess, such that if the source of some f is something and the target is something else, then this actually gives you a typing constraint. So it says that the meaning of f is some morphism which goes from the tensor product of the meanings of these objects, and so on. Okay, and if my monoidal category is non-strict, I have to be slightly careful about how I bracket this, but it's fine as long as you're careful. It's not a problem. So if I do this, so every valuation can be can be extended, and I'm going to say freely extended, and that's giving away what the theorem says. But every valuation can be extended from monoidal signatures to string diagrams, namely, so if I have a string diagram that looks like so if I have a string diagram which is a thing stacked on top of another thing, then this must mean, oh, I should not use S and T, right? Let's call this P and Q. Then this means the tensor product. And if I have two things to write, then this means their sequential product. Sequential product? What are we talking about? Okay. This is called a fat semicolon, blackboard bold semicolon, because like whoever decided that function application goes backwards was silly. This is function composition in the correct direction. Okay, aka diagrammatic order is also called. And if I have two wires crossing, this means the symmetry of my symmetric monoidal category. And again, if my monoidal category is not strict, I've actually made a mistake, and I need to fix this one, because on this boundary, I need to stick some coherence data saying that I'm going to rebracket the codomain of P to match the domain of Q. But it's fine. It's very tedious. You can get away with it. It's okay. Okay. And so the scary theorem, which is the foundation of this entire thing, says that the category whose morphisms are string diagrams modulo isotopy, aka pulling things around, has the universal property of being the free monoidal category on the monoidal signature. So, in other words, it says that, so let's draw a commuting diagram. It says, so I have my my category of string diagrams, and I have my valuation says that this thing is universal. Okay, cool. So that's that theorem's hard. That takes, in Joel Street, this takes 20 pages to prove, and it's terrifying. But it's also intuitive, right? Somehow everybody knows this without being told it. That if I draw some kind of process diagram, that you can unambiguously turn that into the semantics. The fact that you can do this in an arbitrary symmetric monoidal category is maybe a bit surprising, because there's some pretty weird symmetric monoidal categories. The fact that you can do this in the category of sets probably is not surprising. Okay, so speaking of the category of sets, maybe I should go back and start talking about some examples. So, cool. Everyone okay with this? I was going intentionally quickly there. It would be fun to give a 4-hour course just on string diagram coherence, but that's a different topic. Okay. So some examples of symmetric monoidal categories. Well, say every category with finite products is symmetric monoidal. So, for example, the category of sets, or some. So for the purposes of computer science, I consider the category of sets is basically a quick and dirty model of deterministic computation that brushes aside basically every complication of what it means to be a computation. So the category of sets says that a function is a thing that associates every input to exactly one output without saying anything about operationally how it does it or any things that a function can do besides give you an output. So in the category of sets, we could draw a diagram like this. Like we could say, like we have a set of real numbers, and then I have a squaring operation. I still have a real number, and then I have another real number, and then I could add them together, and that's still a real number, and I could take the sine of that, and that's still a real number, right? And so I've written the function x, y goes to sine of x squared plus y. Sure? And how did I do this? Well, I chopped this diagram up like this, and the coherence theorem tells me that no matter how I pull this diagram around, no matter how I cut it up, I'm going to get the same function. Okay. What else? Oh yeah. So this is in the category of sets and functions. But I could also say that this diagram. Okay. So to be precise, my labels in this diagram are secretly coming from some signature. So going forward, I'm usually going to be sloppy about this, and just when I draw a diagram, there's implicitly a signature there. But I could interpret that signature perfectly well in another category. Okay, I mean, I can give it a silly semantics. I can give it a semantics that doesn't match what you think it ought to do given the names I gave it. But you can give it a sensible semantics in other categories. For example, I could say that R is a Euclidean space, and these things are all smooth functions. So I like to use this notation when I say square bracket, something, comma, something. That's the category whose objects are the first thing and whose morphisms are the second thing. That's notation that becomes increasingly useful when you do high dimensional things. So normally that category is called Euc. Euclidean, so it's Euclidean spaces and smooth functions. So like R is a Euclidean space. This thing has Cartesian products, which matches Cartesian products of sets. So the Cartesian product of R with itself in Euc is R squared. Okay. Cool. Right. And by the way, so kind of when you do example-driven category theory, it's very helpful to keep track of what properties you have at each stage. So set is like the nicest possible category, except, well, it's complete and co-complete. It's Cartesian closed, it's topos. The only structure we might want that it doesn't have is a trace, which is something I'm going to be talking about tomorrow. Euc loses most of the nice properties of sets. For example, it doesn't have pullbacks. Because when you try to carve out subsets of Euclidean spaces, you quickly find that they're not Euclidean spaces anymore. But that's okay. If you wanted them, you would use topological spaces instead, or something else like it. To prove a different point, as well as saying that I can interpret the same diagram in a different thing, I could take the same category but give it a different monoidal product. So set also has a coproduct, which is disjoint union of sets. Okay, what can I do with a string diagram in the disjoint union of sets? So if you're used to thinking about string diagrams like this, if you've seen these a few times, then you're like, yeah, this is fine. Seeing a string diagram in a co-Cartesian monoidal category can trip you up the first time you see it. So let's say I have a real number, and I'm going to test, is this positive or non-negative? And I'm going to go either this way or this way. And if it's negative, I'm going to negate it. And now I'm going to unify these two branches. And now I'm going to square root. So what function is this? Well, this is square root of x if x is greater than or equal to 0. And it's square root of minus x if x is less than 0. So what is happening here is branching. So my monoidal product was Cartesian product. So this says that I have one of these and one of these. Here, my monoidal product is just disjoint union. So when I stack things, I have either one of these or one of these. So for example, the semantics of my greater than 0 question mark function, let's erase that one. I can put semantic brackets here to make it clearer. So the semantics of this must go from, okay, I'm assuming that the semantics of the symbol R is the set R, obviously. So this is going to go from R to R disjoint union R, which happens to be isomorphic to bool times R. And so this is so I'm going to say if it's positive, I'm going to inject it into the first component. If it's negative, I'm going to inject it into the second component. So it's left injection of x if x is greater than or equal to 0, and right injection of x otherwise. So so these two, so somehow these the Cartesian case and the co-Cartesian case are sort of extreme opposites of each other. Examples which fail the universal property of being either Cartesian or being co-Cartesian can quite often still have the vibe of being like one or like the other. And so Abramsky at some point introduced terminology wave style or particle style. So I often say for the Cartesian case is wave style. So what I mean by wave style is when I imagine running my diagram on some input, I can slice through the diagram and I will find a value at every point. So every time my slice intersects a wire, I find a value there. Whereas in particle style, where I'm in a co-Cartesian setting, if I stick some input in and now I slice through the middle of the diagram, I'm going to find a value on exactly one of these wires. So you can imagine, you can kind of imagine putting a particle in here and it has to choose to either go this way or this way. It can't go both. Okay. What's the time? Got 15 minutes. That's okay, I think. Yeah. Cool. Let's talk about Kleisli categories. So if I have a commutative strong monad on set, or in fact on any Cartesian monoidal category, but let's call it set, then it's so M is a commutative monad on set. So its Kleisli category is symmetric monoidal. So to be clear, the Kleisli category is the thing for which its objects are the same as the objects of C, but a morphism from X to Y becomes a morphism of C from X to MY, and these composed by monad stuff. So as long as, this is maybe a bit surprising, that your monad has to be commutative in order for this to be, so, I mean, not to be symmetric, but to be monoidal. So this is very unfortunate because there are lots of extremely interesting monads on set that fail to be commutative that we care about for computation, like the list monad and the state monad, for example, are just two examples of very important and interesting monads that are not commutative. We can deal with this, but it's a bit unpleasant. You get a thing called a pre-monoidal category, which is like a monoidal category, but worse. So for the purposes of this course, I'm going to pretend that all my monads are commutative. Yeah? Yeah, okay. So the idea is, so I like to think of these things as effectful computations. So if M is a monad that describes the type of effects that your program can do, then its Kleisli category is something like a category of effectful computations that can do effects described by that monad. So my favorite example is probability. So there's a probability monad on set, which takes every set to the set of probability distributions on it, and in order to not have to think about measure theory and go to hell, I say finite support probability distributions. Put probability distributions on X. So in other words, finite linear combinations P1 X1 plus dot 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 plus Pn Xn such that the sum of the PIs is 1. So that gives you this admits the structure of a commutative monad, and if you work out what its Kleisli morphisms are. So what is a morphism from X to distributions on Y? This is a probabilistic function from X to Y. Or to say it a different way, it's a conditional distribution on Y given X. For example, do I have a good example written down? Well, I could have a function from 1 to delta of 6 things. This is a morphism from 1 to the 6 element set in the Kleisli category given by roller dice. So it says that f of 1 is and this is Bart Jacobs notation for working with probability, outrageously stolen from quantum. I don't know if that answers your question. I stole your question by talking about something I wanted to talk about anyway. Kleisli morphisms are effectful functions for some class of effects that the monad describes, as long as it's a commutative effect. Is there another question? Yes. Yeah. Okay. So, yes, it's some bizarre form of non-determinism where you keep track of how many times you made each choice, I think. But you know, I'm cheating here. I'm fitting square pegs into round holes a bit. Not every monad is describing a computational side effect, but it's helpful to pretend that they are because it makes them more intuitive. Okay. So I haven't said what the monoidal product is, but so the underlying Cartesian product of sets. So remember, the objects of the Kleisli category are the objects of the underlying category, namely sets. So you still have a Cartesian product of sets, right? The ordered pair construction. It loses the universal property of it's no longer a Cartesian product. Although it comes from the underlying Cartesian product, it no longer satisfies the universal property. So it's now just monoidal, but this is what I mean by having a wave-like vibe. It feels like a Cartesian monoidal category. If you imagine running a string diagram, I'm now kind of running it probabilistically, but I can slice it and I still get a value at every string when I slice it. Okay. Another example is rel. So rel, which is sets and binary relations. This admits two different interesting monoidal products. There's the one that comes from the coproducts of sets and the ones that comes from the Cartesian product of sets. So the one that comes from the coproduct of sets actually gives you a thing called a biproduct on rel, which is a thing that is simultaneousfor a product and a coproduct in a compatible way. So those are very strange if you're not used to them. For example, if that happens, so the empty set is what's called a zero object of rel, which is simultaneously initial and terminal. And because it's initial and terminal, everything factors through it because we have a unique morphism here. Okay. But rel with the monoidal product that comes from lifting Cartesian products of sets, I call that the tensor product because it doesn't satisfy a universal property of being Cartesian or co-Cartesian, but it's very interesting. And I think of that, in fact, to be honest, I think of both of them as a kind of model of non-deterministic computation. A very, very simplistic model of non-deterministic computation, but it says that, so a relation between I'll draw it like this just to indicate that it's not a function arrow. It's okay, when you're a category theorist, you have lots of different things that want to be called arrows. So you have to invent lots of notations for arrow-like things. So this says that, so a particular relation from x to y, I think of as a program that if I input an x, there's a collection of y's that it could possibly output. So x is related to y means that if I put in the input x, I might get the output y. Okay, I am very, very much running out of time. I want to talk about, as well as relations, categories of spans and cospans, but I think I'm going to kick those to lecture 3 probably, where I'll have a lot to say about spans and cospans. Rel is a Kleisli category, by the way. Rel is the Kleisli category of the power set monad, which is the monad corresponding to the algebraic theory of commutative idempotent monoids. So it's a theory of non-determinism where we don't care what order we make choices in, and we consider making the same choice twice to be the same thing as making it once. Okay. Now, I have failed an entire section on copying and deleting, so I should start this at least, so I can continue tomorrow, Thursday. So in a Cartesian monoidal category, we always have copy morphisms, and we always have delete morphisms. We get both of these from the universal property of the product. So this, in the category of sets, and realistically, we can formally interpret this notation in any Cartesian category. Right, we can do this. We can use the input twice, or we could use it 0 times. These are so important that we give them special syntax. Instead of drawing this and this, we instead do this and this. And these are going to so these always satisfy some extra equations that says that they form a commutative comonoid. So what's a commutative comonoid? So here it says on an object, and the object is labeling all of these wires. So it is a thing like this and a thing like this, satisfying some equations. One says that if I copy and then I delete, one of them is the same thing as doing nothing, and that's also the same as copying and then deleting the other one. One says that if I copy and I copy one of them, that's the same thing as copying the other one. And then the commutative, so that's what it means to be a comonoid, is these 3 equations. And then to be commutative says that if I copy and then swap the two copies, it's the same thing as copying. So how many minutes do I have? 1. So there's a major theorem. So although I motivated this by a Cartesian category, we get many examples of this in monoidal categories which are not Cartesian. So for example, in the Kleisli category of probability, in fact, in any Kleisli category, we get these things. I'm going to talk a lot more about them tomorrow. By tomorrow, I mean Thursday. And the theorem, might as well end on the theorem, right? Says if so C is symmetric monoidal category, then the following are equivalent. Equivalent. The first thing is that every object. Maybe I need to make another definition before this. Oh no. Oh, it's not working. Okay, I'll come to the theorem first thing next time. But what I will say is that if we have a comonoid, we can present this a different way. The other way that we can present it is to say that we can branch n ways, including 0. So if we branch 0 ways, that's like delete. So you can see that I could define these kind of recursively from these, and because of these rebracketing equations, it doesn't matter which one I choose. So I can equivalently define a commutative comonoid in this unbiased way of saying that I can copy n times for any n greater than 0, and then the equation I get instead is like, if I copy one of the middle ones, it's the same as copying even more times. Okay, I did not get through quite as much stuff as I wanted, but that's okay. These were not timed very carefully, so we'll survive.